This is chapter 6, problem 5. It says at a ball game, consider a baseball of mass m equals 0.15 kilograms. That falls directly downward at a speed of v equals 40 meters per second into the hands of a fan. What impulse Ft must be supplied to bring the ball to rest? So the impulse F times t, and I should write that actually in the front. So impulse Ft must be supplied to bring the ball to rest. If the ball is stopped in 0.03 seconds, what is the average force of the ball on the catcher's hand? Now we're supposed to figure out what the impulse is. The time is given, 0.3 seconds. 0.03 seconds. So time is given, but they're asking for the impulse and they're asking for the force, and with just that one equation, with having two unknowns in here, it's not going to work. But there is a second equation that says that the impulse is the change in momentum, delta m times v. Notice that the units would be the same, kilograms meters per second, and this one here is Newton seconds, and when you resolve that into mass times acceleration times time, you also come up with kilograms meters per second. So the change in impulse, well, those numbers we have given, it's 0.15 kilograms times 40 meters per second. And I actually don't need that delta. There, get rid of it. I need a little bit more space. This was supposed to be an equal sign. And the difference is the momentum that the ball has right now minus the momentum it has when the fan has caught the ball. Well, at that point it has a momentum of 0, so I just subtract 0. I still write it there to show that we have a difference here. If I didn't write it there, somebody would question, well, what happened to the delta, the difference? Okay, anyway, 0.15 kilograms times 40 meters per second. 0.15 times 40 is 6.0, and the units are kilograms meters per second is the impulse. Now we use that result, and we're going to do 6.0 kilograms meters per second equals the force times 0.03 seconds. And when we do that, I think I will write this nicely actually, in the meaning of that I will do an algebra step. I would have a force equals 6.0 kilograms meters per second divided by 0.03 seconds, and therefore I come up with 6 divided by 0.03. Do that on your calculator and you do come up with 200, and then we would have kilograms meters per second per another second, which is the same as newtons, so 200 newtons, or in the neighborhood of 40 pounds. That's quite a force that the person catching the baseball has to exert in order to, well, catch it. Problem 7, which says a railroad diesel engine weighs 4 times as much as a freight car. If the diesel engine coasts at 5 kilometers into a freight car that is initially at rest, so here we have velocity 5 kilometers an hour, that is initially at rest, how fast do the two coast after they couple together. Notice that they didn't give us the mass of either one of them, but only saying that the diesel engine is 4 times as heavy. Actually, that's sufficient. If we have the ratio of the two to each other in their mass, the answer will always be the same, no matter what the individual masses actually are. I nevertheless like to attach a value to it, so let's assume that the freight car has a mass of 5,000 kilograms, or 10,000 pounds roughly. Therefore, the diesel engine has a mass of 20,000 kilograms, 4 times as much. And as I said, I've made up these numbers just to have some numbers to work with. Okay, the before and after the collision, the momentum is conserved. So before the collision, we have 20,000 kilograms times 5 kilometers an hour, plus the momentum of the freight car, but it's at rest, so its momentum is 0. After they have collided, the two of them are stuck together, so they have a momentum of 25,000 kilograms times whatever velocity. So basically what we're going to do now is we multiply 20,000 times 5, divide by 25,000. Times 5 divided by 25,000, and we come up with 4 kilometers an hour. And when we look at that, that would make sense, because the diesel engine in colliding with the freight car has to be slowed down, so going on from 5 to 4, and because it has much more mass, much more momentum, it's not going to be slowed down that much by the freight car. Problem 8, which says a 5-kilogram fish swimming 1 meters per second swallows an absent-minded 1-kilogram fish swimming toward it at a velocity that brings both fish to a halt immediately after lunch. What is the velocity of the smaller fish before lunch? So we have mass equals 5 kilograms on the big fish, and v equals 1 meter per second, and I may want to label that a plus 1 meter per second because he's swimming to the right. And then the small fish has mass equals 1 kilogram and a velocity that we're supposed to figure out that he's swimming in the opposite direction, that means to the left. So we know it's going to be negative, we just don't know how much. I believe we can already look at it and conclude that that velocity is going to be negative 5 meters per second. The proper way of doing it is to say, okay, the big fish has a momentum of 5 kilograms times a velocity of 1 meters per second, while the little fish has a momentum of 1 kilogram times a velocity of negative something meters per second. And now they collide, and that momentum is being conserved, and that momentum in fact comes out to 0. So after the collision it's going to be 0. Before the collision it's also going to be 0, because the center of mass between the two is the same, and the momentum of the big fish going to the right and the momentum of the little fish going to the left just equal each other, cancel each other. And then we go in here and we figure out, that of course is 5. 5 times 1 plus 1 times negative 5 comes out to 0. So minus 5 meters per second. Problem 9. Comic strip hero Superman meets an asteroid in outer space and hurls it at 800 meters per second as fast as a bullet. The asteroid is 1,000 times more massive than Superman, and the strip Superman is seen at rest after the throw. Taking physics into account, what would be his recoil velocity? Well, the velocity of the asteroid is going to be 800 meters per second, as fast as a bullet. The asteroid has a mass 1,000 times more than Superman's. They don't give us the individual masses, just like before. Apparently, it doesn't matter as long as we have the ratio. So as long as the ratio stays the same, the answer is going to stay the same. Again, I like to attach numbers to it. So let's make Superman 100 kilograms, 220 pounds. You know, he's tall and muscular, which means that the asteroid has a mass of 100,000 kilograms, 1,000 times as much. We're supposed to figure out what the velocity is of Superman, and that should come out to negative something. And then here we have, this one actually should be a positive as it's going to the right. Okay, the momentum before anything happens, the two are at rest, so the momentum is 0 before. After, the momentum is still 0, but the two have to add up, respectively subtract in such a way that we do come up with 0. So the momentum for Superman is 100 kilograms times whatever velocity he has, plus meters per second, I guess, plus the mass of the asteroid, 100,000, times the velocity, 800 meters per second. And now, in order to figure this one out here, we have to take 100,000 times 800, divide by 100. As we divide by the 100, we get rid of the kilograms, so our unit will be correct, meters per second. 100,000 divided by 100 is 1,000. 1,000 times 800 means that he has a speed of 800,000 meters per second. To the left, 800 kilometers per second, 500 miles per hour. I guess I forgot that. No, 500 miles per second. I forgot that negative. And then in the neighborhood of 1.8 million miles per hour. So if Superman had to obey the laws of physics, as we all do, we all have to obey the laws of physics, we have no choice, then he would have a recoil velocity of 1.8 million miles per hour. Problem 10. Two automobiles, each of mass 1,000 kilograms, that's why I chose identical ones here, are moving at the same speed, 20 meters per second, when they collide and stick together. In what direction and what speed does the wreckage move if A, one car was driving north and the other one south? So I would have each one of them a mass of 1,000 kilograms. And then this one is traveling north at 20 meters per second. And this one is driving south at negative 20 meters per second. And when I look at the momentum, it would be 1,000 kilograms. I think we can already see what's going to happen, that they won't move after the wreck, plus 1,000 kilograms times negative 20 meters per second, so 20,000 minus 20,000 is 0, the 0 indicating that the momentum of the two together is 0 before the collision and after the collision. Of course, before the collision, either one of them is moving, but their two momenta are canceling each other, giving us the 0 that we see after the collision as well. So they're not moving at all after the collision. Okay. Part B of the problem would mean that one of them is driving north and the other one east. and then the mass of them is going to be the same. I think we can figure out that the angle will be 45 degrees because everything is symmetric. The momentum of car 1 is 1,000 kilograms times 20 meters per second, so that's 20,000 kilograms meters per second to the right, or as far as the problem says, east. And then the other car is 20,000, of course 1,000 times 20 kilograms meters per second up, or north as the problem says. We would conclude that the direction will be northeast, and because I said it's symmetric, we would come up with 45 degrees. So exactly northeast. Now the momentum, we cannot add them up like this because they're in different directions. One is to the right and the other one is up. So we have to use the Pythagorean theorem just like indicated here. So we would have that the combined momentum after the collision, so the combined momentum after the collision is 20,000 kilograms meters per second squared plus 20,000 kilograms meters per second squared, and take the square root of that. And taking the square root, the units actually, sorry about my square root, will be the same, kilograms meters per second. And this one here would be then actually a square root (20,000) squared plus 20,000 squared. Enter. 28,000. So 28,000 kilograms per meters per second. By the way, we could have also achieved that by saying, well, because of the 45-degree angle, what we have to do is multiply with the square root of 2. So 20,000 times 1.4 comes out to 28,000 kilograms meters per second. And now the wreck has, the two cars stuck together, has a mass of 1,000 kilograms. So as we divide this one here by 1,000 kilograms, we come up with a speed of 28 meters per second. So faster than the two, either one of the two before, but that's because they combined their momenta. Oh, I made a mistake. Whoops. So here we would have to divide by the mass of the two stuck together, which is now 2,000 kilograms, and we come up with a velocity of 14 meters per second. This is a recording for Unit 3 on Chapter 7 Energy to do works on problems. So problem 1 is the second floor of a house is 6 meters above street level. How much work is required to lift a 300 kilogram refrigerator to the second floor level? And so work is what it's asked for, and work is force times distance. In this case, the force is, well, working against gravity, so it is gravity, mg, times d. Well, that looks a whole lot like the potential energy, and of course that's what the refrigerator would gain, is the work would turn into potential energy, and that would of course be mgh. That's just on the side. So the work is going to be now in numbers 100 kilograms times 10 meters per second squared times 6 meters I'm sorry, it wasn't 100 kilograms, it was 300 kilograms. So work equals 300 times 10 times 6 is 18,000 kilograms. Meters squared, that's because of the meters times meters, divide by seconds squared. And because this is all base units, we have the abbreviation joules for that. Okay, problem 2 says belly flop birdie dives from atop a tall flagpole into a swimming pool below. His potential energy at the top is 10,000 joules. What is the kinetic energy when his potential energy reduces to 1,000 joules? When you look at the problem, I believe you come up with right away 9,000 joules. Well, here I'm going to write it down. So the potential energy at the top is 10,000 joules. The kinetic energy on the top is 0 joules. Somewhere along the line before he hits the water, his potential energy is being reduced to 1,000 joules, and since energy needs to be conserved, the remaining 9,000 joules then have become kinetic energy. Now, although it's not asked for, at what height is he actually on the flagpole? Well, that kind of depends on what mass he has, because that figures into potential energy as well. As I write down potential energy equals mgh. In order to figure out what height is, I would need to know his mass. So I just make something up. Let's say he has a mass of 100 kilograms, to keep it simple, 100 kilograms. And we have gravity, of course, 10 meters per second squared. And then we have times h. And then I'm going to erase the PE on the left hand side. Instead, I'm going to write there the 10,000 joules. So then when you divide 10,000 by 100 and divide by 10, you're going to come up with that h is going to be 10 meters, which is 30 feet. So that's quite high. Problem 4 says, this question is typical on some driver's license exams. A car moving at 50 kilometers per hour skids 15 meters with locked brakes. How far will the car skid with locked brakes at 150 kilometers per hour? So the distance is what they're asking for, respectively how much further. Well, the kinetic energy goes with the square of the velocity, and since that needs to be used up in work, in frictional work, so work equals force times distance, and this of course would be the frictional force. Well, if the kinetic energy here is gonna ninefold, because that's what it does with tripling the velocity, the kinetic energy will ninefold. That means that the work will ninefold, and we assume that the brakes are the same in either case. So that number here, the force of the brakes, is going to be the same. Well, that means that the distance traveled will be 9 times as much. So it's going to be 9 times 15 meters, which is going to be 135 meters, or roughly 400 feet. Problem 6. In raising a 5,000 Newton piano with a pulley system, the workers note that for every 2 meters of rope pulled down, the piano rises 0.2 meters. Ideally, how much force is required to lift the piano? I think we can answer right away that would be 500 newtons, because for every 2 meters it's rising 0.2 meters, which means we have 10 strings attached, so the ratio of distance pulled to distance lifted is 10 to 1. The number of strings is 10, and the ratio of force pulled to the weight that is being lifted is going to be 1 to 10. But the calculation would be to say, well, how much work is being done? Well, the work is F times distance, which is going to be 5,000 newtons times 0.2 meters. That's how much the piano is lifted. So work comes out to 1,000 Newton meters, or 1,000 joules, of course. That means that we have to exert the same amount of work, or apply the same amount of work. After all, we don't get a free lunch. We still have to do the same amount of work. Our advantage is that we can apply less of a force, but we have to do so for a longer distance, 2 meters, and we have to come up with the same 1,000 joules. That's what I said. We're not going to get a free lunch. So that means that we have to apply 500 newtons. Problem 8. A 60 kilogram skydiver moving at terminal speed falls 50 meters in 1 second. What power is the skydiver expanding on the air? So here's the skydiver on a parachute falling with a speed of 50 meters per second, because distance over time. If you get that into American units, you come up with roughly 110 miles per hour, which seems pretty fast, which means at this point he doesn't have the parachute on yet. So I'm going to take the parachute away. So he has his terminal velocity achieved without the parachute yet, and hopefully is going to deploy it soon. There are two forces acting on him. One is gravity pulling him down with 600 newtons, because that's 60 kilograms times 10 meters per second squared, but also air resistance, which pushes up on him with 600 newtons, because the two have to cancel each other. After all, he's moving with the same velocity. Same velocity means constant velocity means zero acceleration, zero net force. Anyway, so that's the picture here. The power, this is what they're asking for. The power exerted by him on the air would be the work that is being done due to the air resistance divided by the time. The work is, well, force times distance, or mass times gravity, because that's the same as the air resistance. As we know, it is 600 newtons, 600 newtons. So we have 60 kilograms times 10 meters per second squared times 50 meters, divide by 1 second, and we come up with 30,000. And the unit really looks kind of horrific. Kilograms, notice meters times meters, and notice divide by second squared and divide by another second, so second cubed. And as I said, that looks rather horrific. So we erase these base units and come up with the base, write down the base units for power, which is the watt. So 30,000 watt. Don't confuse the unit of watt with the physical quantity of W for work. This recording for Unit 3, Chapter 7 on energy for the problems continued. Problem 9. Consider the inelastic collision between the two freight cars in the previous chapter. The momentum before and after the collision is the same. The kinetic energy, however, is less after the collision than before the collision. How much less, and what becomes of this energy? The last question we can answer right away, since it's an inelastic collision. Inelastic collision. That loss in kinetic energy, however much that is, loss of kinetic energy becomes heat. As the two are colliding, that energy is dissipated as heat and damage between the two. Okay, let's look at the calculations. We would have to know what the mass is of the two. However, we can even do it without. Kinetic energy equals 1/2 mass times velocity squared, and then that's 1/2 times mass times 10 squared. So that would be whatever the mass is, as I said. 50, 1/2 times 100 is 50 times the mass. Versus when the two have collided, we have kinetic energy equals 1/2 the mass times velocity squared, which in this case is 5 squared. Notice that I left a little bit of a gap there because the two have collided, so the two are together, one in the same system, so we have twice the mass. That's why I left a little gap there. So 1/2 times 2m times 5 squared. We come up with 1/2 times 2 is 1 times 5 squared is 25, and we still have the mass, so m. So we can see that half the energy, half the kinetic energy is gone. If we had attached some kind of mass here, we could have written as follows. We could have said, okay, how about if m equals 10,000 kilograms? Well, then in the first one, we would have 50 times 10,000 kilograms is 500,000. And here, if we have meters per second, we could also write joules for the energy. And the second time around, we have 25 times 10,000, which is 250,000 joules. So either way, if we use the mass or if we don't, we come up with that either way 50% of the kinetic energy is lost and dissipated as heat. Problem 11. How many kilometers per liter will a car obtain if its engine is 25% efficient and encounters an average retarding force of 500 newtons at highway speed? Assume that the energy content of gasoline is 40 megajoules per liter. So when I look at these numbers here, I'm going to come up with that combining these here, then 10 megajoules per liter is actually used for the kinetic energy of the car, while the remaining 30 megajoules per liter is wasted as heat. That's exactly what the efficiency means. Wasted as heat, not off heat. There we go. Okay, let's see how we calculate that. Well, we know that the kinetic energy is 10 megajoules for every liter. I'm just going to leave the liter out of here because at the end it's going to say anyway how many kilometers we're going to make for that 1 liter. So it's going to be 10 megajoules per that liter, and that now is being used up by the frictional force that goes into the work, so frictional force times the distance, and these two here are to be set equal because the kinetic energy of 10 megajoules is used up by the friction, and of course, we could say, well, we're putting that energy into the car, but then we would increase the kinetic energy of the car to 10 megajoules, and the car would be really, really fast, but instead it's simply used up by the work due to friction, and the speed of the car actually stays the same. I just set here highway speed of 100 kilometers per hour. Okay, so here we also have 10 megajoules. And we have a frictional force of 500 newtons times the distance that we're supposed to figure out. Well, we divide the two, so distance equals 10 million divided by 500, which comes out to 20,000. 20,000, and we're in base units, so joules divided by newtons is meters. Remember that the joule is also Newton meter, and that of course is 20 kilometers. 20 kilometers is 12.5 miles. A liter is about a quarter gallon, so we would say, okay, what if the same car here takes on a gallon? Then we would have to multiply our answer by 4. 4 times 12.5 is 50 miles, so per gallon we would get 50 miles, so that's a pretty fuel efficient car. Problem 12. The power we derive from metabolism can do work and can generate heat. A. What is the mechanical efficiency of a relatively inactive person who expends 100 watts of power, so expends 100 watts of power to produce about 1 watt of power in the form of work, again the first W here means watt, while generating about 99 watts of heat. Well, when you look at the numbers, you come up with 1% efficiency. Part A. Part B. What is the mechanical efficiency of a cyclist who in a burst of effort produces 100 watts of mechanical power from 1000 watt of metabolic power, so expends 1000 watts to produce 100 watts, and that of course is a 10% efficiency.